We present a new coupling scheme, an efficient B-spline Lagrangian-Eulerian method for compressible flow, shock waves, and fracturing solids. The fluid-solid interaction, FSI, is a ubiquitous problem in science, engineering, and computer graphics. For the incompressible flow, many previous works can handle solids with large deformation. However, all previous works can simulate bulk solids with small deformations for the compressible flow. This motivates us to create a coupling scheme for compressible flow and arbitrary deformable solids. The pipeline starts with the recorded physical states at a time step. The fluid state is recorded on the background grids, while the solid state is on particles. We conduct a standard particle advection and follow with a particle-to-grid projection for the solid phase. Then, we obtain the passable ratio based on the volume fraction of the solid particles in the background cells. We also mark the solid cells and the interface velocities. The interfaces are treated as moving walls in the following fluid advection step. Next, the fluid velocity field advects the conserved variables of the fluid and reaches an intermediate state. After this step, we are ready to head to the coupling between fluids and solids. The coupling system is formed by a mixed-order finite element method. After it is solved and the post-correction is applied, the fluid reaches its final state. The solid has not considered the interior constitutive relationship, so a standard MPM grid update is then conducted. Finally, the standard grid-to-particle projection is applied for the solid phase. This can be followed with any related post-processes, such as the plasticity treatment. Our method is accurate in several famous validation cases, like the stair flow, the Mach diamond, and the cylinder lifting experiment. We validate the solver's mesh independency on 7 different one-dimensional cases. Our solver is accurate and reliable. Our method supports plug-in-and-play materials for the solid phase. We produce the famous von Karman vortices in this experiment on different materials. On the top, the elastic cylinder bounces around, while the deformation is permanent on the plastic cylinder. Next, we soften both cylinder stiffness and let the flow breaks them apart. The elastic cylinder restores the straight shape, and the deformation is permanent on the plastic cylinder. On the top, we detonate a bomb inside a plastic pumpkin and fire a cannon at a weak plastic truck. On the bottom, we strengthen both materials to highly stiff iron. Note the deformation becomes permanent and sharp at the edge. Our mixed interface treatment also easily handles tiny subcell solid pieces. In the supernova case, there are 1 million particles and tens of thousands of fractures. Most of the tunnel will be blocked if we treat any cell with tiny pieces as pure solid. With the mixed interface treatment, our solver handles the case perfectly, and the shock can bypass cells with tiny solid pieces. Tuning shockwave animations can be tedious in non-physical methods. Our solver can simplify this by controlling the Mach number, the ratio between the flow and the sound speed. On the left, a sequence of gradually increasing Mach shock impinges the airplane. The airplane holds the leading 2 waves and is smashed by the last one. We can also control the Mach number of a firing bullet, let it be supersonic, transonic, or subsonic with a silencer. Here are some additional demos. We impinge rocket jets at 3 happy koalas. Look how they are happily flying around in the sky. We create a tri-bunny test by detonating in the center of 3 different bunnies, the iron, the yellowish heavier elastic, and the bluish lighter elastic. Far from the nuclear bomb center, the storm destroys a cactus forest. A landmine ambushes some VIPs. Note that the tires are elastic and easily torn into the sky. The body is iron, which takes some permanent damage but still holds most of its shape. In summary, our work features 3 contributions. A novel compressible flow solid coupling scheme. A simple yet reliable interface treatment to handle the scattered fractures. The plug-in and play support for arbitrary kinds of solid materials.